to our workshop regarding OPeraTIC-FABULOUS project. Our idea is to record this session, so I would like to know if all of you agree or if we record the session or better. Anyone against the recording? No? Okay, so then we will proceed with the recording. ¿Tengo que hacer yo algo o ya lo hace? No, that's okay, perfect. So now I will start. Welcome to our workshop about OPeraTIC-FABULOUS project regarding dynamic beam shaping. We will have very nice presentations today here with us from the state-of-the-art about dynamic beam shaping provided by Pablo. Also, we will focus on FABULOUS, Metamorpha, and OPeraTIC projects. This will be presented by Francisco Gontaz, Audrey Champion, and Pablo Romero. And then we will have also the opportunity to know more about SLM solutions with SLM solutions with the presentation from Sebastian from Kiowa. In addition, we will have also the point of view from an end user, that's Romain Guesdon, sorry for the bad pronunciation, from Fricota. And then we will have all of them in a nice discussion here to know more about potential markets, potential applications of dynamic shaping in general. So please, Pablo, if you come here, then you can start with your presentation about the dynamic shaping.
Okay. So, good afternoon. Yeah. See. Okay. As I will make a general presentation in lack of expert on the research of advancement. I've been a researcher experiencing the need of the beam shaping, and I will talk about that a few years ago. I was young, and I've been working in mainly laser welding in AIMEN. That was the first application of laser in AIMEN. In all of the applications I've been working, there's always the need of going beyond what the laser can do in general. Keyhole welding was our first application. Keyhole welding is very interesting in terms of speed, penetration, improved absorption, so the usage of energy, but has a number of issues. One is the tolerances, the other is the metallurgical issues, the limitations with the very big thermal tensions you produce, the thermal history into the material, which yes. Okay, which produces produces a very dynamic pool, metastable, which is prone to defects, and also very fast cooling. Let's see if this works. Yes, it works. Where in certain metals, the trapped liquid in the middle concentrates all the dangerous elements, phosphorus, sulfur, and so on, which produces tendency to cracking, and all perfectly aligned in the same area. It lowers also the solidification temperature. So from the very beginning, we encountered certain problems, very nasty and dangerous problems, like, for instance, the tendency to cracking. Also, when using a laser heat treatment, which was the second application we used, you have the problem of concentration of heat. You always have thermal problems which come from the design itself of the beam propagation in a stable resonant, which is the Gaussian beam propagation. Has a lot of advantages. It's easy to manage optically. It's has very large depth of focus compared to other types of beam propagation, but it has issues in concentrating all the heat in a point and producing this type of problems. We know where's the origin of the cracking problem, for instance, and we know that some people solve it by introducing a second laser or another heat source to compensate the distortion introduced by the laser. Okay, so one option is to divide the laser into several spots and then work like that. The problem is they are quite far apart to do it with dual spot optics or things like those. So there has been lots of work in reproducing something that in laser beam welding was originally very exotic, which is a combination of multiple sources, one for processing and the other for compensating the problems, but was common practice in electron beam, because electron beam has the ability to shape your beam in any way you want. So they normally used peculiar beam shapes to compensate cracking, to generate cleaning, all types of simultaneous processing. So there was the dream of, okay, if I can not depend only on my resonator to create a beam that makes my job of not only welding fast, but also cleaning at the same time, also compensating the distortion, also avoiding the cracking, all at the same time in an optimal way, that would be fantastic. There was not such solution, and we were working around for years and just dreaming, while other people were developing. So in the last 10 to 5 years, there has been a lot of development pushed by this need, by this demand of the laser processing community of solution like this, flexible enough not only to produce a certain distribution, but to change it when you detect a modification of the conditions that demand a modification of the beam distribution. And that's what's called dynamic beam shaping. And so change on the fly the distribution of the irradiance of the laser on the working surface. So that's for macro applications. But of course, in micro applications, we have a number of other completely different needs. One very important point is that every milliwatt in laser micro applications is costly. we want to take advantage of every watt of power, and there's with the Gaussian bin you have surplus of unused power or superfluous energy that generate undesired effects. So that's one of the ideas of bin shaping. Other is with the increase of available power, you can increase productivity, but routes based on higher repetition rate have certain limits and end up not taking a full advantage of short and ultra short pulse lasers. So for applications like mesh filters where you want hundreds of thousands or millions of holes or spots, that's parallelization or special bin distribution that make all the work at once make more sense. In this case, also the proximity effects are important, though I'm advancing both interesting points and also limitations of bin shaping. You can either make a shape that produces your final result, or make a shape that reduces some issue or problem that you are generating, like accumulation of heat, like generation of bars or some kind of defect. The difficulty is always double. One, to know what's your ideal beam shape. The second is how you get it, of course, from a real laser source. So, as I said, we will have a presentation from Kyo about the ideas either to produce a certain shape and generated by single laser beam pulse impulsion, so to say, or generate a pattern that then you can extend to a complete workpiece. Okay. The one possible way to face the beam shaping is just using a mask. What has been done forever in excimer laser, for instance, just a mask which is slit or a square or whatever, the shape you want, and image it afterwards. It's possible, but it's loosey. It means you take only 30% of the area of the beam. You take only 30% of the power, and the rest is lost. We, as I said, want a solution that takes the maximum advantage possible of the available energy. And that's why the selected or the more desirable solutions are the ones based on wavefront control, wavefront shaping, which means you take the whole or the maximum amount possible of the energy of the input laser, and you transform it into your output distribution. And you can use it for a number of things. To generate the desired distribution of the workpiece on the focal plane, which can be a spot, a square, triangle, your shape, or a combination of several shapes, like the ones we've seen in the workshop from for welding, for instance, that it makes the welding and the heating and the preheating and post-heating at the same time. You can control diffraction or extend focusing or produce some kind of effect that improve internal processing. It's not only for surface, it can be for volume in glass or in applications like drilling. Or you can, which is extremely interesting. Divide the beam into multiple beams to work faster or to work better in the sense that you process several passes. Typically in a laser process like engraving, you make multiple passes, and the first one are stronger and the last one are smoother. You make all of them at the same time, and you take advantage of being all of them close enough so that the material is in the right conditions to take advantage of the energy much better. For instance, the residual temperature or things like those. You adjust the distance in your benefit. All that can be done with a single tool, which is a wavefront adjustment. You have a single input, which is a Gaussian beam, ideally a perfect collimated Gaussian beam, and you end up with some whatever distribution you want or you can calculate actually. There are several ways to get that in principle dynamically. One of them is coming from maybe the realm of astronomy and astrophysics and so on, which is the formable mirrors. You directly shape the wavefront by shaping the mirror that reflects the laser. So the areas of the mirror that are farther back, they are delayed physically in a very simple mechanical way. You can use acoustic modulators, which typically are elements that are used for controlling the power or energy in lasers. But you can shape beams by using them as diffractive elements. And if you cascade, you have one for the X and one for the Y. And it can be acoustic or electro-optic also. And you can use this multiplane light conversion, which is the system used by Kylax, which is a phase purely reflective phase plate, which in each reflection has a small and controlled modification of the phase, and several techniques are inspired by biological microscopy, like generate phase contrast, which has special filtering that transforms phase into amplitude contrast, which we have been playing with in the lab some time. There are several reasons why there's this other technique of special light modulation, which is liquid crystal based, which makes it superior. One is its very high resolution, which the formable mirrors are not able to do. It's very, very flexible in terms of the where you want your phase map to be, how you wanted your phase map to be from 0 to 2 pi, which is exactly the same. Okay, from 0 to pi of rotation in any point. The resolution is now in a few microns for the spot. The feeding is excellent. And it's easier to calculate and control than AOMs or EOMs, of course. And while MPC can be dynamic, it requires a huge lot of expertise to calculate and the multiplying plate, and at the end it will stay the same all the time. So LCOS is the one that provides more, it's the closer to the dream of, okay, make me the distribution I want, exactly the distribution I want. There are other solutions like interference patterning that are simple to calculate, but it's like one trick pony. It makes just periodic patterns, and it makes it very well in a large area with very high efficiency of the energy input. But if you want something that is not a purely periodic pattern, you cannot use the LIP. And there are other types of solutions that are called dynamic beam shaping, but actually are more like dynamic focus control or dynamic extension of your manufacturability, which are great for certain applications, but are not so as flexible as we target in projects like the ones we are dealing with in this workshop. So you see there are lots of techniques. All of them are great in some applications. We are not talking only about the laser manufacturing. They are using communication, they are using data storage, they are using in medicine, microscopy, whatever. But there's an important limitation of SLM that has limited its use up to now in certain areas of laser manufacturing, which is the power limit. All the reflection-based beam shaping, mirrors, deformable mirrors, micro mirrors, and this MPLC can handle huge powers. But SLM was limited by the liquid crystal itself and the packaging of the liquid crystal. There has been developments in the last year, and we are now launching ourselves into the realm. We are users of this type of technology, and suddenly we saw there's excellent prospect for us. Of course, the problem is lasers has always been pushing also for its higher and higher powers, shorter and shorter pulses, always pushing what is physically feasible with handling with SLM. But we are in a very sweet spot now that we can make multi-beam parallelization flexibly and modify a number of things. So SLM has improved here, and also it's improving more and more in the refresh rate and in the number of pixels available and so on. So as I said, there are many advantages of SLM, and the reflective SLM types, even though they have to go through the liquid crystal, can handle pretty high, up to 100 or even farther than the 100 watt limit today. So for microprocessing, excellent. And resolutions are being extended a lot. The response times are pushing higher and higher. Well, response time smaller actually, and yes, they are developing more and more. As I said, okay, if we have a tool that can handle our input beam and can provide your output distribution, the problem is we need to calculate the phase map. And if we want to respond quickly to changes, we need to calculate quite quickly, and it is not an easy task. Yes, theory, the Huygens, principle of diffraction and all the knowledge of how the diffraction works to calculate this type of objects that are the phase maps that transform one energy distribution, the input, into the other energy distribution, the output, after the focusing optics, or after duplet of focusing optics. It's always important to note where we are in an optical system. Algorithms to calculate are available. You can download a Python script and it calculates for you. But it takes time, and it's not always taking into account the real optics and the real characteristics of your equipment. And we will have a presentation on precisely that. We had this morning this presentation from Sebastian, that it's important to take that into account, and normally the algorithms by themselves are not taking that into account. So there are a number of techniques. One is iteratively making Fourier transform and putting some restrictions on the calculations, and that's what you have in your libraries around, and they take forever to calculate if your pixel size is very small, but they end up in a deterministic, always the same phase map. There are techniques that for multi-spot generate certain phase combinations of phase map for each one of the spots, and that works. It's an interesting way to generate parallelization. For instance, one of the computer-generated holograms identifies the deflection, and the other the focusing. So you can have different spots with different energy at different positions, and we have more general optimization that are being developed, which are non-deterministic, which are improving progressively the results using gradient descent or any optimization technique. These kind of techniques are being boosted by AI lately, and they can be used to define the final shape, but also to correct things in the optics you are using. So you have quite a lot of development in this area. I just wanted to show that this is a big area. It's not just using, there are several pillars. How you want to use your beam distribution, how you can transform your input and your output, and how to effectively calculate the best way to generate the beam input in the output. The interesting thing is that different techniques can generate, even one single technique can generate multiple solutions to the same problem, multiple phase maps that generate the same output. And that can be interesting, actually, because one problem of projecting a laser is you have interference patterns, you have speckles, you have areas in the projected image that are not perfect. If you project several of them, if you need to make several repetitions, for instance, you average all of them, all those problems, and you smooth out the result. So you can even take advantage of these different techniques producing different results for the same target output. And there are some new developments, like using multiple SLMs in Cascade to produce special light distributions, like distributions that keep the shape in very long propagation, or like distribution that keep quite well the effectiveness and the final distributions, even if there's some degradation in the input, like misalignment or yes, errors in the input bin. And then there are much more sophisticated developments in temporal effects that are being exploited in the project that will be presented later on, and I don't have time to explore. I'm very sorry, but as the wavefront and the phase front are not exactly coincident, you can even take advantage of that to have very interesting effects when you are processing with femtosecond laser or very short or very wide spectral composition of lasers. So I hope I didn't scare too much, but I just wanted to say that it's a very wide area with lots of things happening at the same time, lots of unsolved problems, but a huge lot of contributions from researchers to improve material processing. So that's all from my side. Thank you.
I don't know if any of you has a question for Pablo, because he. But yeah, we are just in time, so no problem about that. Okay, we will continue with our next presentation that will be provided by Francisco Bondad, the coordinator of Fabulous project. So he will explain beam shaping in the 3D microfabrication environment.
Thank you very much for the presentation, Ariane. It is good afternoon, everybody. I will try to do everything lighter because after 2 days of conferences, everything is started, and I guess if I keep it too hard, it's going to be difficult to follow because everyone will get asleep. So I will try to get it to do it as fast as possible. So yes, in this presentation, I will speak a little bit about how we use dynamic peak shaping for real application, for 3D microfabrication. And this is something that we do in the frame of the Fabulous project. The Fabulous project has the goal to fabricate 3D beta surfaces that enables to produce a new series of high efficiency optical products. We want to tackle this problem with different point of view, different approaches, something that we will explain later on. And we have a very good consortium made of 11 partners, which provide different expertise to the project from different areas. For example, AIMEN, we are the leader, the technological coordinators. We work as well on fabrication of the meta surfaces, together with in collaboration with high-level instruments, with IMT, Atlantic, with FORTH, with the Greek Research Institute. We have some partners which are in charge of the design of the structure that we need for these optical meta surfaces, which are PlanOpSim, FORTH as well, and IMT, which collaborates together with PlanOpSim and FORTH, developing these structures. And we have Fraunhofer, IISB, which help us develop the methods, the illumination methods, to fabricate better structure, because they have a very strong background in the use of conventional lithography, on the simulation, on the fabrication of structures with conventional lithography, and that brings us an expertise which is really interesting for us. We have some end users that are going to validate the technology that we developed in the project, which are Thales, Ficosa, and Stellantis, and we have Modus, which is helping us with the dissemination and exploitation task for the project, while Iris is in charge of the life cycle analysis of the technology developed within the framework. So, as I mentioned, we have a complete approach to this problem, which starts with the design of the meta-atoms that we need for the fabrication of the meta surfaces. Not only the designs of the meta-atoms, but how we distribute these meta-atoms on top of the surface to create the optical function that we need for the different applications. Then we have the fabrication, the actual fabrication. I will explain later on why we decided to go for parallel fabrication, but we are going to do parallel fabrication of this structure using two-photon polymerization, which is one of the techniques, fabrication techniques based on laser that allows us to fabricate structures with lower resolution, or actually higher resolution, smaller features. And as Paulo mentioned in his presentation, sometimes it's not only the things that we project, the things that we illuminate, is how we illuminate, how this light interacts with the structures that helps you produce better structure, better features when you are working with a laser to produce any kind of structure on top of a surface. So with this approach of design, optimization of the fabrication process, develop of the fabrication process, the goal is to have a printed metal surface that has the optical function that we intended to provide. So we have three use cases that will be where we validate the technology developed in the project. One which regards the fabrication of high efficiency solar cells for high altitude platforms. The other use case is the fabrication of better optics for sensor and cameras that can reduce the size and the weight of these optics that are used with the cameras, with the sensors, enhances at the same time the functionality, optical functionalities in collaboration with some other functionalities, like, I don't know, change of bendability or more mechanical robustness, something like that, that can bring not only an optical improvement to the optical piece, but also some mechanical or technological enhancement of the behavior. Finally, we have an additional use case which deals with the fabrication of better optics for the use of for the fabrication of day running lights in automotive industry, with the aim of reducing the amount of LEDs that we use for illumination, having a more efficient illumination with a lower consumption of energy of the batteries. This is of particular importance on the case of the electric vehicle. Those are the use cases. Those are the results that we expect to have by the end of the project, but not only, because we want to develop some to apply the development that we are producing from the experimental point of view to the machines that will be industrially fabricated and sold in the future for producing at the same time these meta surfaces that, as I mentioned, will have some additional and very nice applications. This fabulous project comes from an earlier collaboration with some of the core partners of this project, which was in the frame of the Phenomenon project, where we started to develop new optical surfaces with very good functionalities and exploring the possibility of using dynamic V-shaping to not only enhance the productivity of the two-photon polymerization technique, but also the resolution of the things that we can fabricate with this technique. So in order to provide some idea of which are the problems that we are facing in our project, the first thing that probably should be useful to do is to explain which is the technique that we are using. We're using a technique which is called two-photon polymerization, which is based on the non-linear absorption of light. This means that in order to induce a change in the material that we are illuminating with our laser, we need to induce an effect which is induced by the collaborating effect of two or more photons. So, in the case of, for example, you look at here, I don't know if you can see my pointer. Okay. Can you? No. Okay. Okay. Oh. Okay. In the case of single photon processes, the energy of the one single photon is enough to induce the change on the material, the change that we intend. In the case of the non-linear process, we need more than one photon to induce the same change. This is really interesting because instead of inducing this process on the whole air volume that we are illuminating with laser, we can produce this change in a very small volume, which is called voxel, that allows us to fabricate structures with a very high accuracy. And this is like painting with a small pencil instead of using a very large brush that doesn't allow you to produce very thin lines. So with using this technique, with this nonlinear technique, we are able to fabricate the smaller things than the things that are usually fabricated with single photon techniques. So in order to fabricate 3D structures, the thing that we want to do, that we need to do is to move this small pencil inside our resist to fabricate point by point, voxel by voxel, with this small point by point, the 3D structure that we want to fabricate. For example, in this slide, we have an example of the fabrication of a small spring. So we have to follow the shape of the spring to fabricate this kind of spring. If we use one single spot, we can fabricate one spring, and if we use multiple voxels at the same time, we could fabricate hundreds, thousands of boxes of springs at the same time, improving the efficiency of the technique. But this is something that will be into later. So as I mentioned, we want to fabricate different structures following the designs that are our designs from the Fabulous project. So the main idea is to fabricate a structure that can be used on top of a surface with different features. And the basic structure that was defined for this project was the definition of different columns with different sizes, heights, and diameters that provides, as Pablo mentioned, the change in the phase of the incoming light. So by modifying locally the phase of the incoming light, we can produce a different optical function by changing the range of the beta that we are fabricating. I know it's a little bit complex. Sometimes even I don't understand what the ticket is. It looks like magic, but it works. So it's a nice thing that we have a lot of nice design people in this project that help us designing and fabricating this kind of structures. Coming to the core of this seminar, which is the use of dynamic V-shaping techniques. In the previous project that I mentioned before, phenomenal started use with the fabrication of these nanostructures using diffractive optical elements and spatial light modulators. These elements can be used to produce the light, to project the light in a very efficient way. So you can have a very nice distribution of light with the pattern that you intend to have. The problem is that, as we discovered in this project, having a correct, perfect distribution and uniform distribution of light inside the resist doesn't mean that you are going to have a very uniform distribution of structure fabrication with this technique. Because of effects like the proximity effects, the structures that are close together one to the other, induce a decrease on the polymerization threshold, which in most of the cases produce an over polymerization effect. If we want to decrease this effect, the first trials that we did was to try to decrease the energy density that we were using to the minimum possible. We were improving the size and the dimension and the resolution of the things that we were fabricating on the central part of the sample, but we discovered that even if we had enough optical density theoretically on the edges, we didn't have enough power to induce the complete polymerization of the whole projection. So it was important not only to have a very good uniform distribution, but also to tailor the way we were projecting the light in the resist. So in this project, in collaboration, as I mentioned, with the Fraunhofer Institute, we designed a new way of projecting the light, distributing the light in a different way, in a more adaptive way, suitable way to have not the same optical distribution of light inside the receipt, but the same result what we have, what we were projecting and washing out structures. So the goal is not to project the best or the more uniform pattern, but to have the best pattern possible when we finish the publication. So in collaboration with IMTA, Fraunhofer, and Tanapsim, we designed a new illumination protocol to have similar structures in different places when illuminated with parallel beams. In the case of AIMEN, we're working with special light modulators. So as Paulo mentioned in his talk, there are several ways where you can use the spatial light modulators. The most common ways to work on Fourier configuration, that I will explain later on, and the other way possible is to work on imaging configuration. In the imaging configuration, on the screen of the SLM, what you are projecting is your target pattern, and you project the exact image that you are projecting on the SLM on your resist. So you can have the illumination of the pattern with the same pattern on the resist, and by illuminating different spots, you can produce the 3D meta optic that we are designing. In the case of the Fourier configuration, what we have to do is project the phase map on the SLM, and then through Fourier optics, what you are projecting inside the resist is the target pattern, which will lead to the fabrication of the meta optics. Were designed in the beginning by the design. So I will go just quickly over this. There are, as Paulo mentioned, different algorithms and way of the phase maps that are used for the fabrication, for the projection of light with different patterns, and these different methods, different algorithms have advantages and disadvantages that, depending on the patterns or on the way you want to fabricate, will be more useful or less useful for the fabrication. Now I will start with presenting the results of things that we were produced here at AIMEN with our setup. The best thing that we started to study were the projection, how to project in a better way the pattern that we were, let's say, projecting on the SLM. So we were working on two configurations, as I mentioned, imaging configuration and Fourier configuration. On the image configuration, on the left column, you have the targeted pattern. on the right side, we have the projection that we have in our system. So the projection of the of our target is very similar to the intended light distribution. So this doesn't seem to be a problem for the fabrication of 3D metasurfaces with this system. So in the let's say in the ideal case, everything should work very well. In the case of the Fourier simulation, we have the same results. I mean, the projection seems to be quite accurate with respect to the targeted structure. So by changing and tuning the optics in that way, we are able to project the patterns that we intend inside the system. So if we project these patterns, these are samples of the images that were projected. Okay. Now, in this video, I hope you can observe that we can, with a single flash, we can fabricate the structures with the pattern, with the side pattern, having different structures with different shapes and different sizes. So this technique is quite effective for the fabrication of these kind of structures, and we can control in a very good way not only the shape, but also the size and the position of the things that we are projecting. Because if we change the shape of the things that we are projecting, for example, in this video on the right side, we can project, again, fabricate things that are really similar to the intended pattern, which is the one on the top side of this slide. So we've started to look at the limitation of the limits of this technique. So the first thing that we wanted to do is to test if with an SLM, by adjusting the pattern that we were projecting and the laser parameters, we were able to fabricate things with different heights. And we were able to fabricate about the height of the structure that we were fabricating, having a similar shape, like in the rectangles on the left side of this slide. On the other part, we wanted to understand also if we were able to fabricate the structures close to each other with different sizes and different heights and different distributions. So we started to project patterns, everything in image configuration, as you mentioned before. So different arrays of spots with different separation, different numbers of circular areas were projected and fabricated with this technique. If you look at the SEM images on the right side of the slide, we can fabricate these patterns, and the structure seems to be larger in some cases, which is the case when you have a longer exposure or a higher laser power, a larger dose, irradiation dose on the sample. You can change the tailor to the size of the structures. In fact, by playing a little bit with these two parameters, these experimental parameters, that the laser power and the irradiation time, which leads to a different irradiation dose, we were able to change the size of the pillars that we were fabricating from a smaller dimension of 600 nanometers up to 3.5 micrometers. There were some strange things, issues that were appearing on this kind of structure where we were over-polymerizing the resistance. This is due to the fact that I mentioned before that when you have when you don't have the correct illumination, you can reduce the polymerization threshold in areas where you don't expect to have some light. But even with a small residual light, you are able to produce some strange features. And so the fabrication is not as reliable as it should be. So by changing the way you project the light, by producing, for example, the amount of light that you project on the center spots, you could enhance the feature that we're fabricating and having the objects in the same positions, but with a better resolution. We tried some other tests to study the repeatability of this fabrication approach in image configuration of different structures, annular structures, square structures, the log of AIMEN, arrays of lines creating different shapes, and everything was quite reliable, quite repetitive. In fact, the fabrication of the structure was quite similar on different areas of the sample that we were fabricating. We tried to do this kind of things, combining different points of the sample, providing different micro images, for example, the logo of AIMEN filled with different features. And with this, still the repetitivity of the technique seems to be quite good. Looking at the scanning electromagnetic images of the samples, we observe the same repetitivity with different features that were fabricated by repeating the flushing on our patterns inside the resist with good size, shape, and positioning control, leading to the fabrication of larger areas with a very good and regular pattern. So in summary, I hope I can convince you that a good light distribution of by using spatial emulator can lead to the fabrication of regular structures with a very good resolution that could be useful for the fabrication of optical metasurfaces. That the fabrication of the optimization of the fabrication processes needed to get these structures in the best possible way. That this beam shaping can increase not only the resolution but the size control and maintain a very good repeatability of the process for larger areas. And as I mentioned, as part of this development will be introducing industrial machines. This is expected to be industrially available in the future with applicability for highly demanding optical applications. Thank you very much.
Thank you. So we will skip the questions until the end of the session. Okay? So our next speaker is Audrey Champion from LASEA company, and she will introduce us the Metamorpha project. Okay. So you're small, but and everybody can hear me. It's okay. Yeah. Okay. So yeah, I am Audrey Champion, so engineering project from LASEA. And actually, it's my colleague who was supposed to present this presentation, but he wasn't able to come. So then I replaced him. So I don't really know that I get all the part of the project, but I will try to do an overview. So Metamorpha project name is made mixture micromachining with laser beam tailored in amplitude and phase. This is the beam shaping. So at first I will explain a little bit the project, then I will explain the integration of different components in our machine. We speak about the beam shaping, and then industrial use case. Then we made a conclusion. So at first the goal of the project was to manufacture a single agile USB, so contractor pulse laser
macro machining platform with an integrated galvo scanner. So this we want to replace manufacturing process chain, for instance, for milling, cutting. We use EPM, ECM, and wet chemical etching, so this is not good for the environment. So then we want to use all the process. So in this project, we develop full control over phase and amplitude based on two SLM in cascade. So this I will explain a bit later. And it allows digital beam steering from vertical structure boards. So then we have to visual laser process, electric or digital, and we use a 3D sensor data and machine learning algorithm. And then we have inline process control using real-time feedback from photodiode to control the quality of the sample, for instance. So here we have three industrial use cases to answer different manufacturing challenges. So emphasis on energy reduction and increased recycling, sorry, and quantified sustainability assessments, so in terms of environmental and socioeconomic. So here we have three use cases. So Philips, for instance, they need to manufacture small metal parts, so that it's complex and fragile, and they need very high precision. Then with T-Central, they manufacture large area conventional rollers, and they want to rewriting old rollers, for instance. And then the Ceratis, they manufacture a very hard carbide parts, and then they need to do automation as well. So here we have 12 partners on this project. So we have IIT from Germany, Lazard from Belgium, LWTH from Germany, UPV from Spain, Vivid from Germany, DPX from Spain, Tantis from Spain, TPS from Germany, Ceratis from Luxembourg, Philippe from the Netherlands, and Alain from France, and Force from Greece. With so actually a series of mechanical and electronic operation are needed for the moment, so polishing, milling, verification. But then they use electrical discharge machine, machining, electrochemical machining, and wet etching. So as I told before, this method provides excellent results, but there is a lack of flexibility, cannot be easily adapted, and then we have a negative environmental impact. So harmful process chemical, waste product, high energy consumption, and minimal manufacturing options. So then that's why we want to use laser. So here, each electromechanical process can be replaced with ultra-short pulse laser process. So here, according to the pulse duration, we can reach more or less a good quality. So for instance, if we have a long pulse duration, like 150 nanoseconds and 10 nanoseconds, we have a certain process. So we have excitation, then we have melting, then we have vaporization, that lot of melting, and as a result, then you have full melted parts one piece. So then if you reduce the pulse duration in using femtosecond laser, for instance, or picosecond laser order, then you have another process without thermal effect or minimized. So then you have high precision, minimal thermal impact, and processing of particle, particularly in metal, to non-linear absorption, because of then you can machine almost all materials. So then the inconvenience here is that you have a low renewal rate because it's smaller. So then the cycle time is increased. So here, just to a variety of elements is to show a little bit what we can integrate in the machine, so the components to machine. So you have the X and Y stages movement, so but this is very slow. So then we use a galvo scanner, most common. 80% of the industry are using this scanner because you need to get 10 speed. Then we can use as well polygon scanner, but the problem is unidirectional, and but then the speed is quite higher. And then finally, it's possible as well to work with locations, cylinders for cylinders. So then, in Asia, for our part, we are integrators, so we integrate. So this is an example of the machine, and then we ensemble, integrate everything. So a mechanical part, electric cabinet, software to control all the machine and devices by software developed by Asia here. The granite to avoid the vibration. It's important, an optical component, cascade SLM in this case, because and galvo scanner, axis, and laser. So before integrating everything, we need to test in laboratory each component. So for instance, here we can test, for instance, the modules with two SLMs. And then you have the photo of the final machine for the mechanical project. So then, to do beam shaping in this project, we use dual SLM configuration. So then, it's possible to have an arbitrary distribution, energy distribution. So here you have an example of a butterfly. So they can reach quite a complex beam. Then you can have a dynamic terrain loss process optimization in real time. So then you can change in calculating the phase mask, sorry. And something interesting as well is that you can elongate the elongation of the machining zone in that direction. So this is important when you are using, for instance, for the wall, you have vibration, and then you need to extend this Z distance. So here we can go over a few centimeters, which is huge compared. We have usually with the femtosecond phase, it's more like 100 micrometers. You see a big difference. So this is to be integrated in the optical part. So then you have the laser, you have the collimation, so with a beam expander to have the proper size of the beam at the entrance of the module. Then you have the two incidents creating the proper shape. And then we image this shape via the theta lens and combine with the galvo combination. So here with this system, we are suitable for any arbitrary shapes. So you can create what you want. You can work in single spot, or you can work with a multi-spot to do regularly arrays, for instance, arbitrary pattern. So this allows a make-to-measure process. So then here we can control the incident, the angle of incidence of the focus laser beam. So we're using the SLM, so we can voltage it at the entrance of the lens, and then it will change the angle of the beam on the piece. And so then you can choose your angle, and then we can as well have straight vertical walls in choosing the angle to compensate the natural opacity that you have with laser beam in general. So this is an example of angle laser application from here. Here, we need to have a very vertical wall, so we have a defect for the performance of the gear, for instance. And this technology can the optics part that need to be integrated. We have an example here of prism. This is not easy to align, so with this system, we have something easy. So here we have two sensors. We have an inline monitoring system. So it can analyze data in real time during the machining process. So then you have immediate feedback on the machine progress. And machine learning based framework that predicts surface fineness during the laser process. So so then so you can cover the piece in time. But you measure this kind of food. So if you have a sample of the defect, then you can cover it. Then we have another system here that is offline. We use a scanner. And here you have an example of the topography actually. And then we compare this topography. We review the topography after machining. And if it's okay, then it's okay. And if it's not okay, we can rectify the piece. So finally, we have a user case here, Sudan and Philips, for instance. They need a very high precision, high tolerance and demanding shape. Currently, they have different processes, so wet chemical etching and electrochemical machining to cut slots, second SEM to provide the surface finish. So then, with metamorpho, the target of the metamorpho here is to elimination of 3 chemical processes, avoid offshore waste pollution, and energy consumption reduction of for the process. Regarding system, so they fabricate a large wall size, 2 meter length and 0.8 meter diameter, and they want to inscribe a very small, small structure on this wall, like 10 micron, about an average. So it is very precise, and then it's not possible for no things of wallers is currently possible. So then with the metamorpho project here, we have a method expedition, low river process, energy consumption reduction, and multiplied by 10 the lifetime of the. Then finally, sales artists. So they are manufacturing ceramic furnish for polishing and embossing. So it's an extremely hard material which are very difficult to machine. Currently, requires 3 electromechanical processes: electron milling, electrical addition machining, manual polishing. So repair of microstructure of warm punch is not possible. So then with metal project, we want to avoidance of all waste production, massive cut down in time and cost, and energy consumption reduction, like 90%. So as a conclusion, with this platform, so with laser machining platform, we want to replace conventional manufacturing process chain. We have full control over phase and amplitude using true Cascade SEM, so digital reading steering and arbitrary intensity profile. Let me measure laser process. We have a linear process control using real-time feedback from photo data. And then we have 3 use cases. So manufacture small parts, small metal parts, large embossing walls, and variable ceramic. So thank you for your attention.
Very much for the presentation. Our next speaker is Pablo Romero, now as acting as a coordinator of OPeraTIC project. And he will introduce this project to all of us.
That's it. Yeah. Hello again. Yes, I will just present the project. It's a project where we reuse another one. But I will also first talk in general about the project, and then talk about one of the results, specific results, where we were studying the effect of using SLM-based parallelization to improve one of the texturing of projects. Of the project applications. So it's a project for improving the usage of high-power ultrasharp lasers, high-power femto and picosecond lasers, because they are in the market. There has been a lot of money and effort to put in making them work and making them bigger and more capable, but there's actually not real industrial systems that take advantage of hundreds of watts because of many issues that I already introduced this last year when presented the project. And during this year, we have been advancing in getting some solutions to improve the use of a particular laser we have in the project, which is a 100-watt picosecond laser, and also testing on high-power femtosecond laser. The idea is, yes, of course, to take advantage of the very specific capabilities of ultra-pulse lasers, precision, low heat input, and so on, and improve the productivity in one of the many ways there are to improve the productivity. One is just going as fast as possible with higher repetition rates. So if you keep a few tens of microjoules of pulse energy per pulse for keeping the resolution and reasonable irradiation on your focus, going to many going from hundreds of kilohertz to megahertz of repetition rates. It has a big problem. Either you go really, really fast in scanning or moving your workpiece or whatever, then you might lose control of the position of energy, or accumulate a lot of pulses and lose benefit of cold ablation. In either case, not good, because your target is to keep productivity, to gain productivity while keeping resolution and precision. So the other way is going to higher energy per pulses and distribute the energy per pulses in a smart way. So either going like that for higher watts, or like that for higher watts, higher pulse energy. High pulse energy in a small focus loses some of the benefits because you are well over the threshold. If you increase the spot size, you lose resolution. So the only way is multiplexing, so parallelization. And that's interesting for a number of applications. The main application we are targeting in our project is surface texturing, and going beyond what you can do with a typical 3-axis machine or 2-axis machine, which is flat surfaces. So going full 3D surfaces like propellers, aerospace components, with things that are really, really curved and not fully defined. So we want to develop all the components to do that. One of the components, of course, if you want to arbitrarily distribute energy, is shaping. Not only that, we want to develop all the modules that allow for this to happen, and the different modules are, yes, in shaping. Sorry, 1 second. Yes, the laser itself might be commercial, but we want to transmit the laser energy. In some cases, modify it, amplify it, or stretch it, or whatever you need. But in any case, transmit it through optical fiber, which allows you to move in full 3D, which is a big challenge of the project. Second, shape it in the way you need to get the maximum advantage of higher energies transmitted by the fibers, and then focus and oriented through the workpiece, including quality monitoring and so on. Sorry, sure, this is the last. Yeah, this is the last. Sorry. The main elements we have been developing with different amounts of success It's the fiber itself that transmits the energy, and the parallelization unit, which is a modular system from Kyoto, which will be presented afterwards, linked to the scanner. I will not talk about this; it will be the next talk, but about how we use it in certain applications. The main issues for maximum advantage of an SLM system, you need a linearly polarized beam. Out of a standard optical fiber, you get a randomly polarized beam. The photonic tools beam is non-dispersive and keeps a reasonably elliptical polarization, which can be used for relatively high efficiency of the transmission of the linear component of the polarization, and then use it in this element here. So we could get hundreds of microjoules to parallelize in multiple beams and get things like those, several beams to process. Otherwise, photonic tools is working hard on a fiber that keeps all the energy in linear polarization, which is extremely difficult. There's this problem of easy damage of the fiber, trying to keep the mode through the transmissions through all the fiber is a whole fiber complex to operate, and we are pushing them to get that result. In the meantime, we are developing the system as a whole and the processes that get advantage of this parallelization. And the idea is to be able to texturize large components, full 3D, like elements that are inside of dishwasher, washing machines, anything that handles water, to make them hydrophobic, to reduce the amount of lost water and the amount of water needed for washing or drying cycles. That's very important. You could have huge savings, especially in energy and in water itself, while reducing chemical treatments, as previously mentioned. The second is aircraft composite, reducing manual labor to improve painting or adhesivation. The third is texturizing die components, forming for automotive industry, so big parts for reducing the effort, the energy needed, and the scrap material, and elements for lighting, which has similar applications like in Fabulous, but in larger elements with textures which are also bigger. So we are targeting 100 micron to tens of microns of texture size, different from Fabulous, which was targeting much smaller elements. So I want to show our results when testing small pattern parallelization, when in a very particular case, which is this one, trying to get hydrophobicity with just different scanner patterns generated with SLM. And the idea is we use SLM because we can switch patterns, we can test multiple patterns, we can change distance and composition of the energies of the pattern, anything very quickly from one test to the other without changing the optics. And the idea is on stainless steel to make those patterns, to make a low temperature heat treatment to stabilize the oxides, and then test the contact angle, which in the base material is a bit over 80 degrees. Not enough to guarantee a quick drying of the stainless steel. So when you generate with single spot patterns lips, you can increase a lot the contact angle, but still it's not over 150 degrees. So if you align the polarization and the pattern in a way that it's simply the same as moving with one single spot, but in 4 spot, you accelerate the process, but you get the same result. It's the same type of pattern. But you can do a few things. You can put the patterns in the other way. You can put the polarization in the other way. You can mix both parameters. You can use the patterns to make the repetitions one on top of the other very quickly. So the lips formations are interfering with each other, and you can repeat the process in lines or in grids. And when you repeat in grids, you have a very interesting effects that the lips are not anymore aligned exclusively with the polarization, but are getting affected by the pattern directions. So you are using the previous lips as initiators of the growing of new lips. So the effect is that you get a smaller special period and shorter structures, which is exactly what you want if you want super hydrophobicity. And as you see, we got over 150 degrees, which is what is considered super hydrophobic instead of just hydrophobic. So as you see, we can get different type of patterns. Some of them are extremely good in getting high angles. Some are very good in getting these random, pseudo-random distributions of lips structures. So what you get by simply putting 4 beams and changing them in distribution and in patterns is multiplication of your design space, which is good and bad. But because then you have lots of things to test from now on. But you have variable amplitude, very small secondary amplitude with fixed primary period. So it's a very, very interesting result that is not attainable with a single spot repeating, even though you make different patterns. It's the beams working one after the other immediately are getting farther results compared with single beam in the same patterns. So we can get either improving much more the angle, or improving much more the productivity, or getting in the middle by using those combinations in the new design space we have with this combination. And that's just the beginning because it's only 4 spots. And we got to more complex arrangements of multifocal distributions. We will get more complex possibilities to design microstructures. So that's our next step. We got already results over 170 degrees of contact angle, which is huge, which are stable after some time. Well, it's stable, which is a typical problem of laser texturing, and with higher available energy, we will go to higher number of spots and then explore larger design space and see if we are able to not only increase either productivity or contact angle, but both at the same time with this new type of combinations. And that's all for myself. Thank you.
Okay, we are almost finishing the first part of the workshop. That is all these presentations. Okay, our next presentation. Our next speaker is Sebastian Landon from Kiowa, and he will explain the current solutions on hardware, software innovations.
Well, thank you for the introduction, and hi again for most of you. First of all, I want to thank the previous speaker because they mentioned almost everything. Yes, there is a large R&D topic into using SLM for beam shaping because there is real need in terms of application. The good news for you is that we are doing that to have industrial customers getting access to that without the need of doing the R&D. That's exactly our job. And so both all the presentation that were made just before are exactly aligned with what we are doing at Kiowa. What I want to share with you today is the state of the art and what we can provide. There is plenty of things to do now, and OPeraTIC is one framework for us to work with AIMEN on the optimization of multi-beam patterning and the use of that for laser processing. But what I present today is what to do. So what is can be bought by industrial right now. It's a bit different from the application we've discussed before because we are more in the marking application right now and concern more focus on marking time reduction. So that will be the core of my presentation. But again, still open and active in this R&D unit. Okay, so I will present you again, maybe for those who were there this morning, Kiowa, a bit more detail there. What we put behind the multi-beam laser processing approach and how we translate that into actual industrial products. And to finish my presentation, I will give an example of a process development we've made in a micro drilling application using the module product. So first, Kiowa. Again, the idea is not to reduce the full story of the company, but just have in mind that it's a quite young company. We have been in the field for 15 years now, and basically, like I would say, any startup, starting with an AD, founding the R&D stages from local funding first, then European funding. So OPeraTIC is one of them. Is another I mentioned this morning. And currently we are in this time where this R&D time is switching into products and also to next step R&D. it's been introduced, so I won't spend much time on that, but current technology using laser is, of course, based on using galvos in most cases. And there are actual limitations to do that in throughput and efficiency. And in particular, when you want to use high power ultra short pulse lasers, because high power is in general associated with high repetition rate, thus need high speed movements in terms of scanner. And you are reaching the mechanics limits, basically vibration, inertia, and so on. So getting a higher speed is not that easy. There are techniques to work on that, such as the external scanners, but it's hard to have that working. And plus, as we mentioned, as previous speaker mentioned, this setup lacks of flexibility. You have a Gaussian beam, the one that's given by the laser, and you have to do with it, basically. So what we do at Kira is adding an optical component, an optical module inside the laser chain to give access to dynamic beam shaping in both kind of application. The first one is process development, because when you develop a process, you discover things and you have to adapt the need or want to adapt the beam pattern. And example on this superhydrophobic surface that Pablo just showed is a good example. There is room for optimization here. But for any kind of application, then we also need to maintain this kind of performance. And in time, your laser may have variations, your setup also, and the whole technology we use is give access to these kind of corrections. And of course, that was the core of my presentation this morning. This is software control, meaning that you can develop feedback loop, AI control, and so on. So really compatible with this Industry 4.0 that's targeting the OPeraTIC project. Not only. So what we provide is dynamic beam shaping. Again, we've seen that a lot this afternoon. But in a way that is parallelization of what is actually already done with a single beam. So do not change physics. We only give access to 2, 3, 10, hundreds of times doing the same thing. Currently, we are working in 3 different field of applications. The first one is surface treatment in general, but mainly for decoration. I will show some example of application using multi-beam technique to reduce the speed of the marking, and mainly in the traceability application, so internal and external traceability. So the main difference between the 2 domains here are who is reading the information that we are marking. So internal, in case of internal traceability, that's the manufacturer itself that follows the product it's been manufacturing for quality control in general. While external traceability is made to have a direct contact between the manufacturer and the end user. So basically you and me, by reading it by, in general, a smartphone. So technically, that means it's a different type of code, more data metric for internal traceability, while it's usually more a QR code in the external product. It's also a question of size. The internal manufacturer wanted to be discrete or even invisible in some cases, while in the case of its external, it has to be easy to see, easy to detect, and easy to. In both those fields, we are also using the multi-beam approach to introduce some anti-counterfeit features, meaning that the marking can be read, it gives information, but it also gives an insight of if the product is a real one or a counterfeit. Some example of these 3 fields. So on the left, you have this decoration. So this example is a film bottle, so glass perfume. And using this multi-beam approach, we can make this large size marking with very high resolution, very high image quality. So that's a gray level marking here. Hopefully you can see that. We will be able to see that more in detail on the shared presentation after the workshop. Still maintaining a marking time that is compatible with industrial demands. And using the multi-beam, we have demonstrated that we can go 5 times faster than using a single beam with the same industrial system, so the same capex at the beginning. For internal traceability, so we are marking small codes, and we'll go deeper into that afterwards, but the main interest is speed. We can do those codes very fast, faster than a single beam, and so it's quite easy with the multi-beam approach to address 7/10 of thousands of parts per hour. So it's very high-speed lines, average line, pharmaceutical lines. To translate that into marking time, we're considering tens, hundreds of milliseconds per mark. So it's very, very limited. And for this kind of, the code is bigger, so basically the marking time is a bit longer, but you can still achieve high production with large applications such as this kind of electrical breaker here. So we are talking about some tens of thousands of parts per hour. And again, we can increase the speed compared to a single beam approach by a factor of 3 to 5. Another example, but to emphasize that even though we are splitting the energy, we do not forget about quality. That's an interest. We maintain the quality that's achievable by using a laser and a neutron source laser in particular. So in the case of marking, the quality is captured by the grade of the code. I don't know if that's the notion that you are familiar with, but grade A is a perfect grade. Grade F is very bad grading. And so we've demonstrated in this pharmaceutical application compatibility with million parts per year with the grade A and B, so very good quality and almost perfect conformity reading. So with that, you just add a module into the system, so the investment is not that high, and you get a productivity increase multifold. So of course the ROI is very fast. So how to switch from one to another? So again, this is, and you are all aware of that, how to use a single laser system. You just add into the design a multi-beam pattern, and you've seen in the OPeraTIC installation that it basically a laser machine with a specific head at the end. And you choose the right multi-beam pattern, you create a library, and depending on your application, you'll load the pattern you want to use. And you keep the same way of dealing with the scanner trajectory and so forth. Just adapting the frequency and pulse energy to the process to be realized. And by doing that, in most cases, you can in fact avoid making non-necessary movements by the scanner, and that's how you make it faster at the end. Because, as mentioned, we are dealing with the limit of mechanical movement in the scanner. So if we move those movements, the scanner is still in its high-value zone, and we gain from the polarization. So we have developed two kind of techniques, and that comes with two patterns families to use a multi-beam pattern laser. The first one is what's called full stamp. That's the idea of stamping. So basically, instead of marking each single dot one by one, right, on a traditional approach, you stamp the full image with a single laser dot. And as you can imagine, The more dots you have to mark, if you can do that in a single beam, the more efficient it is in time conserved. In this application, we can target small codes, so a few hundred of microns. Again, one beamlet here is the traditional laser beam, so you still have the resolution of the laser, you still have the interest of the production-wise use of the laser, so no consumables, non-contact. That's exactly the same, but you are doing several input. The second approach is made for increasing the size of the pattern we can create. So in this first case, we are dealing with millimeter scale codes. In this second approach, we can go up to centimeters or a few centimeters code size by doing a stamping of part of the code. The approach is called pixel stamp, meaning that each laser should mark a pixel, so a square, as an illustration, and you reproduce squares to create an image. So that's the idea of pixelated image. By using the dynamic beam shaping, the interest is that on the same machine configuration, you can choose actually each pixel, being a small one, a bigger one, a triangle, any kind, depending on what you want to do at the end. Still, getting from one pixel to another is given by the speed of the scanning. Okay. In terms of using that into production, again, very close to existing laser approach. Existing approach, you basically program a scanning job, and the scanner is setting the right laser parameters, power, frequency, and stuff. And once you have a job, you mark it. In our case, you do exactly the same, but in between, you put this multi-beam selection, but you have a library of pattern. That's how the software works. We'll see that briefly. You load the one you want to use and do the same as you. So this approach is, of course, integrated into actual products. We have two types of products at Curva. The one on the left are the system, so they provide the marking or the texturing function, meaning that inside the system you have the right laser because the laser profile is different from the one you have to use with a single beam. You have the causal head and all necessary optics to have full function in marking. On the left side, that's the one we are working with in the OPeraTIC framework. You have the module approach that integrates into a laser chain the beam shaping function. So that's a more flexible one, but that gives you access to changing the pattern, but that is to your job to develop the necessary beam shape. And of course, we are here to learn. We have several variations, I won't detail that, but depending on pulse duration and wavelength range, we adapt the product. Just to mention the main limits of this approach currently, because it was introduced before, we can manage currently on an industrial approach up to 100 watts of laser power and up to tens of millijoule of energy in the infrared and visible range. We are working on increasing the power because more power is more throughput, and currently we are working on doubling the power capacities of up to 200. A main interest also of the system is that everything is controlled by the same software. It's called BeamForge, and inside you have everything that's needed to actually get the pattern you want. This means that inside the software, you can define the multi-beam pattern you want. You have several tools to do that and to do that very rapidly. And then you have every necessary calculation to control the SLM that's inside of one product. So every work, every optimization of this algorithm is, again, what we offer. You don't have to manage the complexity. And everything is installed as compatible with integration into laser installation. So for instance, we manage XY location, rotation, so very, may say, low-level function, but are very pragmatic. Also, the software allows to synchronize every component in the chain, being the laser, the scanner, and the SLM, to make full sequences of marking, meaning that you don't need different software to control. We can provide the overall control of the system. So inside the software, that's a few examples of the types of multi-beam pattern you can create easily. So of course, to decode, we can mention that we work quite largely in the traceability application. So basically, sorry, it's very small here, but you give the content of the code you want, you give the type of code you want, data metrics, QR codes, and so on, and the software generated for you. And of course, that's a very there are rules to generate the code for them to be readable afterwards. So that's embedded into. Sorry. So you can put pictures, numerics, and you get the code idea. There is also a very flexible and versatile tools, what we call PixMap. So you basically have a grid and you can activate or deactivate the dots and set different ratio of energy you want to achieve with the dots. So that's most probably what was used to generate the 1x4 and 2x2 matrices that Pablo just showed. It can be used to generate this kind of this pattern here, having a first beam with a high level of energy, then two beamlets with a lower level of energy, and then again an even lower level of energy for the third line. And depending on the application, Pablo mentioned for welding, for instance, the need of having a major beam that welds and secondary beams that helps controlling the thermal effects. You have the opportunity to create what you need and to explore. And yes, calculation time is a question, but just to configure there, calculating one pattern in the BeamForge default configuration is 100 milliseconds. So basically you click, you get it. And it's on the system. It's not only calculation, it's also displayed on the system. So you can switch from one to another very rapidly, explore. And in fact, what takes time is not necessarily making the laser processing with the multi-beam pattern, is identifying which one. So making the methodology, to get the results of this work. But you can automate the generation of data very, very, very rapidly. Okay, so again, this three-step approach. And so not to go into too much detail here, but you define the pattern, then you save the configuration. That's a file on your computer. Next month, you want to reuse it, you load it, and back to the configuration we defined. What's very important, particularly into drilling application or micromachining in general, is to get the same results, so the same level of energy in each beamlet. What you have on the left here is a typical result you can get from raw output from state-of-the-art algorithm that calculates a multi-beam pattern. So you have discrepancies in energies in the optical distribution that leads to discrepancies into the size of the drill you are creating. By using this PixMap fine-tuning capabilities, you can reduce these effects. currently this optimization is made manually, but still on a few steps approach, you can reduce drastically the difference in size of the general estimate. And of course, as it is software control, you can automatize this kind of operation. And that's what we are doing in the VOLC project. That's an internal project that AIMEN providing an automatic feedback loop to get the actual result you need of this kind of uniformity by setting this kind of definition and data. Not this kind of shape, but this kind of, if you are actually seeing my there. So this is the raw output of the software, and this is the raw output after feedback loop optimization. Another aspect that's embedded into the software is the beam quality control. When you use beam, depending on the technology, the beam quality may be good to less good. Embedded into the software, you have functionalities with simple clicks when you can switch to the row. So you see my picture again. Here it is. So the raw beam characteristics, like you can see on the top line, that's what you get from a single beam installation, roughly, to a corrected version. So you do that once, and that's what we do at manufacturing. So when the system is delivered, it's pre-optimized, and you then have access to the second line. So very high quality circular beams, and as I introduced this morning, you can get a better depth of focus, meaning you don't have to put the sample at a very precise position in the C-space. That's the idea and the work that is being done, that is under the OPeraTIC project to actually optimize its beam quality, so not having the user to set the right parameters, but just having a click that generates a software optimization. And so first results were presented this morning, and if you have want to go deeper into the topic, I'll be fully available. Again, once you've done this optimization, you save the file and you just reload. And this takes a few tens to hundreds of milliseconds. So on the R&D stage or application development stage, very, very fast. A quick overview of where multi-beam have an interest, because it's not a solution to everything, of course. There is, of course, a very high interest when you are dealing with high processing speed. I mentioned some figures previously. So high-speed lines, speed of more than 100 meters per minute, we can address that. Typically roll-to-roll context. There is also an interest when you want to achieve high speed and high resolution or high precision in the location or distances between the shape. Because as you are dealing with a stamp, the distance from one beamlet to another is independent on the movement of the target. While if you are using a single beam, you have to synchronize precisely the movement of the target with the actual shoots, and that's the difficulty of the mastering the resolution in high-speed applications. And as it is compatible with femtosecond and several wavelengths, it's very applicable to technical substrates such as polymers that have highly nonlinear resistance. Okay. A few examples again of where we are working. So beverages, very high lines, electronics, very demanding technical material and high speed for some of them. Luxury is more about very fine marking and very controlled one, so high quality standards. And for most cases, we've seen so far technical substrate based on glass. That is not the easiest material to process. Compared to technology, so more for the machine builders, of course, if you are using low power and low energy laser source, multibeam cannot do anything there. We are dealing with parallelization. We need high enough energy to make at least 2 dots. If not, the parallelization has no interest. Of course, the best way is the best region is when you have high power and high energy, meaning that you can parallelize much and you can do it fast. And in both intermediate cases, high power and low energy, or high energy and low power, that's a good region also. And multibeam can offer high energy. And to illustrate the interest in ROI effect, that's the representation of the cost of 1 watt for a laser, depending on the number of watts that the laser provides. So basically, the more watts you apply, the less the marginal cost is. So if you can use those watts, that's of course of high interest, economically speaking. Just to finish, and I'll go quickly on that. Maybe this one is not the highest interest. So a real case where multibeam technology was applied. So as mentioned at the beginning, we are talking about a drilling application. So here you have a piece of plastic that we were willing to drill with 44 holes with 2 different beam diameters with the same marking and the size. So each hole is between 10 and 20 micron with a target precision into the diameter in the range of 2 microns. And we want to do 1 piece in less than 1 second. Okay. So at first, we of course explore the single beam approach. And we have identified that using the energy, we can determine the diameter of the hole we can create. So that's the traditional process work. But we also identified that increasing the pulse repetition rate, the quality is decreased. Then, with this starting point, we work on the definition of the multibeam pattern to be used. So the first approach was to decompose the marking into 3 steps. The one you have at the bottom of this slide. So first step, drilling the external line, circle. And so each laser should make one of the 3 circles to be made. And at this first stage, we introduced the advanced correction we have in the software to reduce one of the most known limitation of using SNM is this central spot energy. And you can see here that it was reduced from a very, very significant contribution down to almost nothing, the 90% reduction. And you can see on the image next to that the effect on the material. So we had marking at the very first step, and by using the software control we are able to make it disappear completely. By using this first approach, we generated a batch of samples that the customer could analyze, and we discover every real-life problem in application development. So problems in the part itself and the polymer modeling, problem in the process strategy, crosstalk with thermal effect, and so on. So you can see here a zoom on a very specific effect when 2 beamlets or 2 drills are made together. They are crosstalks, and you can see that the quality of those drills in particular are poorer than the others, and every kind of real life. But the interest is that using the same installation, using only software programmation, we were able to start from this initial step of a three-step approach of drilling, and by iterative work, converge down to a five-step approach. And this was done only in weeks. Basically, one step is 1 week of work, 1 week being adjusting the optical parameter, setting the brush, making prototypes of tens of samples, providing that to the client so that they can analyze, give us feedback, and can initiate the next step. So basically, in 1 or 2 months, we can converge to this very different stage at the end, and this was allowed by software control initially. And at the end, so if we compare the initial step of process compared to the final one, we reduced marking time, even though we increased the number of steps because of an integrated overall strategy to the machine. And we achieved the targeted precision required, so meaning 100 less than 2 micron in the variation of diameter for each dot. And this so translate for a single machine, the comparison with a single beam approach would have required 3 to 5 machines. Very different, but basically without the multi-beam approach. So more throughput, the cost, an investment divided by 8 for the customer at the end. Flexibility, because the customer itself can learn how to use the machine and adjust the parameters and make other step development by their own. And everything, thanks to the software, very simple, because the client learned to use the machine in only 1 week. Very simple. That's all for today. Thank you for your attention.
Thank you very much. We'll continue this. Here, the last presentation from today. Our last presentation is given by our next speaker is Roman Beton, sorry, from Picosa, and he will provide a different point of view as an user of this potential technology developments through photon. No, fabulous. Thank you.
Yeah, so everyone, I'm Roman Guidon, tech lead at Picosa Automotive. So for those who don't know, Picosa Automotive is a tier 1 automotive supplier. So we're providing various type of equipment for automotive manufacturer. Among various equipment, I'm working in what we call the ADAS branch, which is responsible to develop advanced driver assistance system. Right now, mainly working on cameras, but it can be various things such as radar, LiDAR-based systems, processing, and everything to help you drive more easily. So, what is our role in Fabulous? We are not directly working with laser for like most of the parts, but our contribution is to work as introduced on one of the use case. So we contributed obviously the requirements definition, helping support the design of the meta surface, so not on the technical level, but more on the requirement and use case driven level. And our main contribution will be hopefully next year to validate and test the produce sample by the project by our partners and validate them in an automotive camera use case. So what are the challenges addressed by Fabulous in our specific use case? So basically, to list a few of the challenges right now is obviously that OEM demands more and more cost-effective, sustainable solution without compromising performance. That's obvious. So in our use case, what we are mainly aiming is resilience to harsh conditions, harsh environments. So we're talking about external cameras. So cameras that can face high temperature, dirt, rain, fog, snow, a lot of things that can prevent all the ADAS algorithms to properly work. So that, and also enhanced night vision based on anti-glare performances. So at night, with the strong contrast and lights, that's producing a lot of glaring that can also highly impact the algorithms. And the use case we are aiming was mainly fisheye capabilities. So having one coating basically designed for us for fisheye cameras. So with the curved lenses, and ideally an all-in-one coating that could answer all our problematics. So improve basically two concrete properties, one being anti-glare, improving the system transmitters, and the other one that we could call anti-fogging, but also anti-rain, anti-harsh weather, which is basically including the water contact angle on the surface of the lens to make it more hydrophobic. The validation that we're aiming to do, once again, it will be done last year, we're still in the middle of the project, is to perform a performance evaluation through our industrial testing protocol to ensure the reliability and the compliance with automotive standards. The idea is basically to benchmark and compare against current market solution, not as an end final product, but to try to highlight the advantages of such nanostructure coating for ADAS applications. So right now, what can we say without having seen and evaluate the final prototypes and samples of advantages and limitation of such technologies in our industry? So the main advantages that already have been mentioned by Fran, first of all is sustainability. So some of the functions I cited previously, especially the hydrophobicity, is right now in the market answered by chemical coating placed on the surface of the lens. And it has been estimated that we could save up to 3 million tons per year of chemicals waste, basically, if replacing these chemical coatings. Ideally, obviously, we also would like to improve the efficiency. That could be done with such a coating that gather multiple functions. Having a multiple functions coating would help to reduce manufacturing resources needed to produce those lenses. And the last one is robustness. Other functions, for example, such as lens cleaning that is required if you get dirt or water on your lens, use it right now quite complex either optomechanical solutions. Those are solutions that are quite fragile, can be quite fragile, and so having a kind of all-in-one solution already implemented on the lens would be a huge help and huge benefit for us indirectly and for the OEMs, obviously. The few limitations that right now we can see, maybe we will discuss in a few minutes. is obviously we are an industry, a company, we're not a research center. So we see a really high potential in those kind of technologies, but we think that research is still, a lot of research still needed to reach required TRL for having automotive level products. We're also working with specifications that can be hard to reach from what we've understood when speaking with the partners. For example, surface size. I mean, we're not talking about huge cameras, maybe like 1 centimeter diameter, which already can be a challenge to print on those kind of surface, and also to handle the curvature of the lenses. Most of the cameras we're working on are wide angle, wide field of view lenses, so with high curve, which can be challenging to the manufacturing of this coating. And the last one is scaling. Scaling at the speed and the printing rates required to be competitive in an industrial is really not easy right now. The things we've seen are like really small, few millimeter samples produced in minutes or hours. So like scaling up to be able to print in a few minutes one lens would be required to be a competitive solution. And that's it. That was just like a small introduction to better understand what is our use case, what is the context, and I guess we'll be followed by the roundtable to talk a bit more.
Please,
Okay.
you can.
After layout.
Yeah, because now we will have here a discussion between all the speakers. So if Audrey and Sebastian, if you can also join us here, also Pablo and Fran. And Pablo will participate in this roundtable, and he will moderate also the discussion. But first of all, I don't know if any of you, if any of you has a question for any of the speakers. If not, okay, so you can start your friends' discussion.
Okay. We don't only water, but okay, that's maybe we're
Sober friends.
sober friends. Okay. So starting from the end, I was very surprised with the figure of 3 million tons of chemicals. That corresponds with which production you have of?
No, I'm not saying. I mean, it's another I took from the proposal of Fabulous.
Okay, this is in general.
I think it's not for artificial level. I think it's. I would assume at automotive level.
Okay.
No. Yeah.
But in any case, you are targeting to reduce chemical treatments and.
I mean, that would be one of the idea of this nanostructure coating is to replace the chemical and to reduce the use of it. I mean, it's something that is obviously asked more and more with the reduction of waste and everything like that. The automotive every industry, I would assume. So yeah, that's the idea.
That's something we have all in common. In that sense, for marking, for instance, what are the competing technologies you have besides single spot laser?
Basically, the most common one for this kind of speed is inkjet. Even though it's also limited in its speed. The future is that we have figured that existing one can manage, let's say, 10,000 pieces per hour. Higher is high-speed inkjet, so it's the same as very high-speed signal. And in this, again, one of the drivers to switch to laser is often the reducing of the waste, because inkjet is not a clean technology. So it's not necessarily bad for the planet. It's hard to turn that into production. And switching from one production batch to another takes some time. There's also a lack of flexibility, at least for the case we were asked to work.
Besides, there's some advantages of laser in durability and stability.
Yeah, at least for the feedback, we have long-term stability of the product itself and its performances. Some lasers are running from tens of years now without any significant maintenance cost or terms availability. So the technology has proven itself to be reliable.
Okay, so laser is faster, the results are better. What is the limit for taking over the whole market?
At least to my knowledge, there are two limits. One has been introduced. It's seen as a new technology, even though it's tens of years, 40, 15 years now. But it's still considered a new technology. It has to prove itself in high industrial application. And the other is cost, not per parts, because it's not seen like that, but there is an investment at the beginning. Getting an inkjet or getting a laser is not the same.
Okay.
Even though if you consider all things together, that's what we are working on in terms of marketing and communication, is to translate a per cost price, and laser is very profitable in that sense. But you are turning CapEx to OpEx. So to explain that's a different aspect from this one.
Okay.
Would you comment on that? That's an interesting point because the question, two questions here is getting the right performances. That's of course the main one. If we don't get that, there are no use. It's not usable. But the other question is giving access to these performances. And to my sense, that's a very interesting aspect in the several projects we discussed together. And OPeraTIC, for the one I know the better, is that it takes into account how to make the per person in the end that we control the machine understand at least partially what he's doing and be able to react. Even though it's not an expert in laser, it's not an expert in multi-beam processing and so on. And I think that's a dimension that is considered, but maybe not largely enough. Because having a technology that if no one can use it, that has no sense. And that's interesting to see that even in European projects, this dimension is present.
Yes, that's something that we appreciate a lot in Kiona, that consideration for the usability, not just the performance. Something that let's say in Fabulous, I really also appreciate and value, so to say, compared to OPeraTIC, is that you have, you mentioned in the presentation, the design embedded in the research itself. And in our case, for instance, the user is on his own to design the function. You have the design of the function, the fabrication, and the process.
Yes, because in the end, everything is connected.
Yeah.
You need what the end user wants. It's an optical function. So you have to work on the definition of the structure that you need for this optical function. There are several approaches to reach this optical function. Purely geometrical, based on diffractive optics, based on the different kind of arrangement of things. And then there is the limitation of the fabrication. Sometimes you have to incorporate those limitations in your model, because otherwise you lose the optical function. And then we are speaking about optics, we are laser experts, but in the end, what you have is the laser material production. So you have to take into account as well this. When you are working with a material, your laser interacts differently with different materials. So everything makes part of the design. You have to take everything together, particularly in the case of two-button binary section, for example, because this is really critical. How your laser interacts with your materials. You have to design your structure. You have to then design your process, see how your laser interacts, how everything works, and then put these limitations or these advantages, these deviations from the model back into the process. So having people who has this knowledge and has a very good approach of taking advantage of this full feedback helps us to develop more powerful tools for the in cases like for the magnetization. Having a strict control of the definition of the structures, the fabrication, how they are fabricated, and put everything in a loop, it's definitely a must for having an optical function which is really reliable for the industry. Everything has to work together, from the material to the optics to the laser to the fabrication approach. Everything has to work together.
Okay. In case this really works together at the end of the project, and there's a complete package of functional design and so on, what's your approach as you concept to use it? Do you want it as equipment to work on your facilities, or you want an external provider to code and functionalize your optics? What's the best ideal business for?
I mean, it's hard to say for sure without analyzing anything, but based on how we work, and I would assume that in the end, yeah, as you say, we might go through a provider, because usually we like camera manufacturers, so we take all the pieces and we bring them together, and then we tune sensors and everything to make the camera. But for example, the lenses, we do not produce the lenses, we do not apply the coating on the lenses. This is something that we get from a provider, from the provider. So because we have no experience with laser and with such complex, let's say, application, I would assume that this would be something that we would have to find ideally with our lens provider. That would be the perfect one if we are a lens provider that also develop in this chain this kind of new technology, or we can co-develop with them and then integrate. That's actually how we work. Like we come with a proposal, or they come with a proposal, and then we try to develop it and adapt it to our specialist. That would be the ideal world. If not, maybe let's say three actors chain with the lens provider, the industrial laser coating, and then us receiving.
If I may, in this case, these machines, we have an industrial partner which fabricates machines for this kind of structures. So we have the people who design, work with designs, with software, commercial software for designing this kind of structures. From technical point of view, from its my perspective, I might be wrong, but this is the perfect tool for developing the kind of meta-optic metastructures. Probably not the best technology for large batch, for mass production, but it's the optimal tool for developing this kind of meta-opticas, metastructures, very nice functions, already find the structures, and then probably fabricate this structure with other. But this is a complete approach to fabricate, to define an optical function, to test it, to see the result, and then probably provide the master for a for application. And that's where the machines could help. I mean, to fabricate the master, to fabricate the function, to probably with the provider or someone who wants to have a new set of optical functions work with this approach of definition, fabrication, parallel fabrication in the sense that we need to fabricate thousands of nanostructures to have this metasurface. So one by one, it's very slow. So if we want to make out of prototypes, this is a good technique, but we need to enhance the productivity. Having several prototypes testing these optical functions is really nice to have a final product that might have the properties that we want in terms of optical function, the ability that it's needed, the mechanical properties, because I mean, those are for camera, for sensor, optical side needs to be reliable. So for me, it's a very good benchmarking technique to produce really good optical devices.
Wish list is pretty harsh.
Yes.
There's lots of things at the same time. But it's interesting that yes, in all the presentations, all the projects, and not only the European project of philosophy in general, what you mentioned of co-development together with the R&D, the industrial small companies that are able to provide technology, and the large companies that give the market requirements, like in our case in OPeraTIC also, seems like a very powerful way to accelerate innovation if compared to single actor driven.
Yeah, as I mentioned, especially with this technology, it's mandatory because again we are working with AIMEN and other partners working on the laser properties, and then you have the one especially working on the designs, the theoretical designs that have to work together, and then we bring basically our needs. We were the end user, so we say, okay, it's about like it's right now finding compromises. The theory, what we want to achieve, and what is actually doing with laser. And so I don't see, I mean, maybe a huge actor like maybe Thales, something like that, and I won't be able to be sure about that, but we will not be able to do that on our own. I'm not sure AIMEN would be able because to do that on their own, and that's produced pressure. And we're working with PlanoC in our use case, who are running all the simulation and the theoretical design, and they are really, really small companies, so they won't also be. And so each actors for that, we need at least the three of us, I think, to work together to get this. And yeah, that's why it's a special project.
The user is really needed because you don't want to lose track of the final aim of this project, which is bringing the industrial solutions to Europe. So we need the key actors in Europe leading us to this to their needs to push us in that direction.
And also, I think that's emphasizing a major trend in everything. In fact, whole have to do more with less, and it's getting more and more complex and technique, and even big actors of manufacturing, automotive, cannot master everything. So they have to rely on other, even small ones that have very specifics, and have to work together to get mutual interesting results. And we've seen that at a very small scale. That's the application I presented. The last one, it was a direct end user to us discussion, and that was the first lasers they bought in the company, and it was femtosecond high energy one.
Okay.
Unreal situation. Using a multi-beam approach to make parallel drilling. So, considering that 10 years ago, it was almost impossible to think it was possible, and we are talking about a major pharmaceutical action, not a peer, small peer. So, I guess that's just an illustration of the trends here.
That's how it's changing.
Yeah. And for instance, I don't know exactly for the FABULOUS or the Confab project, but in the OPeraTIC project, we have lots of different entities. And I think that's also indicating that we need several very specific experience and knowledge to work together. And I do align with what you were saying, targeting a very end user demand. And that's the end user in that case. That's
when we
work on the real problem.
Yeah, because then as we increase dealing with more complex problems, your knowledge is becoming more in a certain area. The other areas still do go together. Example, things that when you're developing a research project, you think that they're not a problem. At the end, you find new problems. So you have to find new solutions for new problems. And the best way of finding new solutions is to work with a very complete approach from people, in our case, from people that has a very strong knowledge of materials and optics and everything. You have to put everything together at the end because everyone brings his own solution to solve the problem. Because a research project always is finding new challenges and overcoming these challenges. And the challenges are becoming more difficult with time. It's hard.
But it's also interesting because in that work, at least to my experience, the major problem you have to address is not the one you expected in the beginning. So this also is emphasize the need of flexibility into the installation, because if you build a machine that's supposed to treat a problem, in fact that's not the real one, then you're stuck. And that interest of the software control stuff and AI and all this flexible and adaptable technologies, I think is a good answer to
having different point of views, because sometimes a solution might come from a different field. Sometimes
Yes, it's interesting how, in particular in beam shaping, it's very cross-pollinized from biology to astronomy to material processing. It's all the time certain solutions that appear in a field and crossing to the other, even if the powers are totally different, the sizes are totally different, but we learn from quite a lot.
Yeah, it's like this idea of STEM application that translated into welding application. That's not at all the same light, basically.
Yes.
But still, the concept is the same. You can try to, flexibility, but also open.
So I would ask you how to make some questions. Yeah.
I have a question for Azea. You mentioned the scenario 10 years ago. So not like go 10 years further, but how do you imagine laser in 5 years? These applications that you showed today. And I know that we are in the state of the art. So how do you imagine the state of the art in 5 years?
It's my view that's difficult because for anyone, what would be next year? Difficult to see, but at least on my side, I am curious, so I am gut feeling that the beam shaping approach in general, not necessarily the one we choose, but will, as Pablo mentioned, open the box to next generation of laser processing using more complex tools. So basically, I would say the same with more complexity, but more complexity requires more experience and more specific one. So technology centers such as AIMEN has their role to explore that and free work to give access to end users on easier solutions. And yeah, I think that for 20 years now, increasing the speed and the throughput was increasing the power by increasing the repetition rate. So we are talking about gigahertz application right now. I think there will be at least work getting to high power by repetition rate, and maybe we talk about terahertz and so on. But I also think that increasing the energy and power utilization is basically the new mainstream, right? So I think that this will take some important place. Laser development.
So have been developed a lot in the laser tubes. The lasers that we knew 15 years ago are not the same lasers that we are using now. We have to learn how to use them faster and better. Yeah, I mean, the price per watt has been cheaper year by year. Now we have very powerful tools for working, but we need to learn how to use them in a more efficient way. In increased productivity, it's always faster, more power, parallel. I think it's going to be several paths. It's going to depend in the application finally, because how you use your laser, it depends on which kind of process you have. So for several processes, polarization would be the solution. For other ones, fast scanning. So I mean, every process is going to be, the improvement is going to be process dependent.
There's something I wish will happen sometime, which is all the caveats and points you mentioned, limitations, like it's still considered new, it's still considered difficult, it's still considered expensive. At some point, we will break those limitations and laser, which has been for many years developing, but it's always running ahead of itself in developing at the same time the lasers, the optics, the processes will provide this solution, which is at the same time competitive, cost-effective, and comparable with other solution. Then we have the all the work of adoption from the industry in terms of yes, understanding of it, design for manufacturing, and the complete package.
And not to mention, of course, greener.
Yeah.
But that's the interest of this 3 projects, because the target is basically the same, and we
All
have real case application to give actual use case demonstration and figures to show that it is reliable, it is, you can do advanced stuff with that, and it's greener indeed.
So that's the question.
Maybe some food for thoughts regarding some of the things you have discussed. It seems to me that one of the main problems in laser transfer of developments to industry is a scaling up, which is always a problem in every technology. And of course, you have to think of several aspects. One aspect is that you try to avoid excess heat accumulation in materials. This is one problem. And it's less of a problem with femtosecond lasers, but then you have problems with penetration depth, with how fast you can do processes if you go to large scale, and the problematic of how you distribute all these. I think what Yoga does is very interesting, and I assume that you have a direct relationship between the irradiance level when you have just one beam, and when you distribute it, then you divide this essentially by the number of beams that you have. But then there's a threshold which affects your heat input and accumulation into the material. And then you need to be above a threshold. Let's say if you're drilling above a certain threshold for ablation to remove material. But maybe you can reach a threshold with one system. But if you want to scale up, usually you will have to think of a number of laser systems. So this is a very important aspect that we always consider. In all the solutions that we find, there is a need to multiply the laser systems. And as you multiply them, each laser system becomes more, it becomes more economic, cheaper. Principle. It's not the same to use one solution with one laser than 10 or 20 lasers. And then the other aspect is that we're always looking for the technical solution. But maybe what will be successful is what we find in our applications, which is the fact to avoid contamination, to reduce energy cost versus the conventional processes, and all these aspects, which are really what will make a difference for a production company. So I think these two aspects, that the fact that you can multiply lasers, you don't have to use one. And the other one is that with all that and with the cost of these laser systems, which is now, as Ron said, is much lower than it used to be. I mean, it's way, way lower now. I think we need to think and discover what is an advantage to industry from these other points of view. And I can give you one example. I know of one system with a company that we worked where the cost of chemicals and disposal of the chemical waste is about 50 to 60 million euros per year. So how many lasers can you buy for 50 euros, for 50 million euros?
Way too much.
And just consider, the selling point is, this is 1 year.
Yeah.
If the cost of the lasers is 50 million, the second year, they're making money.
Yeah.
So, no, this is a very important argument. So I think you should be very positive with the fact, even if with one laser you cannot reach goals, think of many more lasers and what is the solution for the customer?
Yeah, thank you for the comment. We are fully aligned. That's why we are talking about ROI by using multi-beam, because it's a marginal cost that you can cover by the increase of throughput. Still, we are facing a wall, as I mentioned, translating OPEX, so operative costs, into investment. And there is a financial wall, at least in large groups, and the one we are discussing with. It's difficult to move from one to another. It's not at all the same. And we've seen some industrial that are more confident into spending millions per year in consumable rather than a few millions one time in an investment. So there is still a mindset to change there. And that's the reason why I think that actual figures, actual use case analysis, such as the OPeraTIC-FABULOUS and the metamorpho ones, help us having references, public references that has been validated by Europe in general, but a lot of experts to strengthen the communication and help moving the mind change.
I think this is a very good point, because one of the ideas that we have been working with other companies is that to protect the European industry, you should apply these rules in regulations. So we should lobby so that the European community makes these regulations, and whether something is made with a contaminating process somewhere in Africa or somewhere else, should not enter Europe if it does not comply with the environmental rules.
Yeah.
This is the type of things that, because if we only do it in Europe,
we can have the same discussion about CE marking, that's theory, and then you have real life. And there is something in between, and I'm not saying it's not a good idea, but it's not a real life correction. Regulation is of course necessary, but you cannot make everyone change by imposing to change. I think there is more to do there, and part of our role is to find out how to convince rather than force.
but you have 2 European projects here that you're talking about.
Yeah.
So do you include regulation directives in the European projects, for example?
We include proposals for policymakers, which is quite far away from regulations, but it's a first step, yes. And one thing we want to do in the next workshop we organize is to concentrate on one thing, which is this metrics, measuring the not just economic but socioeconomic and environmental impact of the technology, and have all of the projects, not only these two projects, these three projects actually, but the whole Lines cluster, which is a cluster of 7 projects, I think, and all aligned together in using the same metrics and trying to extrapolate it at European level and compare it with our competing technologies, for instance, inkjet, for instance, anodization, for instance, or chemical etching in the case of texturing, or PVC, chemical vapor deposition in the case of optical coatings, things like those. We know we are better, but it's very difficult to compare if we don't have all the same type of metrics.
But maybe you should include regulators in the projects, people who are in regulating bodies. I know some, and you will be surprised where they come from sometimes. And some of them lobby for these things, but they're in a minority. But I think if in these projects, in the European projects, you include regulators as part of the active members of the projects, then maybe this will help.
Okay. So on that note of we have to work together to change the mindset of the industry and use regulation as a help instead of walls. I propose that we end here and thank everybody for the attention, discussion, and your time. Thanks everyone.
Thank you.